pleasure to give the it's a pleasure to give the seminar for Wayne State since all the seminar work has most of it has been doing in Wayne State. So the seminar today will be split in two sections where one will be more on the production kind of a level of the manufacturing. Then we go in the production planning. So feel free to any one of you wants to ask some questions. You are open to, and at the end, I'm having some slides for discussions and kind of present my future directions of research. So my research, um, I hope you guys seen the slide moving. No. Okay. So my research has been focused on circular economy. And circular economy is basically the philosophy of we reusing waste of industrial processes or all the product life cycle and reinsert it into production again through the feedback reverse cycles, which we mainly know as maintenance, reuse, recycling, and refurbish. So this is the main picture of the circular economy here, made from Ellen MacArthur Foundation, and my research has been focused on the right side of this diagram, which all the industrial products, and then which something that the foundation couldn't picture in that figure is that one of the key aspects and the most critical and overrepresented in those processes is the disassembly. So in this figure, we have on the first row our traditional manufacturing where we have the raw material being transformed into a product, and then at the end of use phase product is being collected through the core acquisition or what we call it collectors, and then we start our reverse cycles um, through reuse and manufacturing recycling. So the first key process is the disassembly. Then we do a condition assessment of the product. Then we either separate good products or good components, or either we use those bad components to do recycling. So first step, which is the disassembly, is being the throughput, so it's the bottleneck of all the downstream processes. So this is why I'm focusing so much on disassembly in this work. And then disassembly has been kind of a big theme for research over the past decades, and even more now that Europe has been a big push for circular economy, green um, manufacturing, eco manufacturing, all those things. And now US is trying to keep up, especially with the microchip manufacturing and also the EV batteries. So my research, like I said, has been in two big areas. And for the sake of this seminar, I will call it disassembly production and disassembly planning, even though we have different names in the research, which I will talk about them throughout the seminar. So to start, we have been introducing manufacturing all sorts kind of technologies that we can call it integrated technologies like VR, 3D cameras, collaborative robots, scanning cameras, and all those technologies that we can improve the way we perceive products. But one technology that I'm focused on my seminar and research has been collaborative robots. So why I've been focused on collaborative robots? This sentence here has been to a very famous research in disassembly. And he's saying in 2019 that automated disassembly has not yet overcome the human flexibility, but it's still a great truth for the manufacturing today. So there are so many reasons why. So first of all, remanufacturers or even recyclers, they lack of product data. which makes really hard to automate any type of process. You need some sort of like a flexibility to account all the variability that you have in a product. So either a product comes to your uh, remanufacturing site with a defect or is a different model or is missing one component. So you need to account for those variabilities into your product. And then you also remanufacture also lacks of testing time, which makes all those automation and programming setup phases really hard to implement with robots. So researchers have been using cobots as a way that we can integrate sort of the flexibility of the human aside with the robot by assisting humans on doing really hard tasks or really demanding of labor to accomplish the disassembly task. However, my most of them have been having a hard time to justify how cost effective is this way that we are using cobots. So now I'm trying to focus my research in a different usage of the robot. So as like a learning decoder, whether that the cobot can um, integrate all the knowledge gathered from the human and then repeat it to realize all the complexities that the product has and then replicate in large scale. So to do that, I first started designing what I call a cobot training solution or cobot training station, whether the human and cobot will have some sort of interactions between the cobot programming, and then we have some learning through it that will kind of understand based on the disassembly tasks that we are doing in it. So in that case, I'm kind of narrowing down in two tasks. One is the pick and place tasks, and the other one is the unscrewing. So by modeling those two tasks, we can actually take the cobot script and understand how the cobot path is being performed and identify each of the parts of the script and replicate in large scale. So we are adapting all those um, movements that we learn from the cobot and replicating to other robots so that we can reduce setup time in the automated assembly line. So to do that, I did two sets of experiments. One was in the cyber environment, another one in the physical environment. So for the cyber, and both actually, I used the same assembly model, which was a lead box. Whether we had like a very simple assembly, have two frames, and we had 8 screws as well. So the human would have to handle the cobot and move around each of the component location and then choose either to picking the component or unscrewing the component. As you can see on figures A and the C and D as well, you see some of the balls being placed in a different location in the box, the small box. So imagine that you are collaboratively or programming the cobot to perform the entire disassembly task. And then after you gather the robot two-path trajectory, you can sort of starting laying out all those particular time space time points, whether the human choose to be unscrewing or picking place. So if you can pinpoint that on the program after you um, start executing again, so it's an offline learning that you are identifying on the robot trajectory, which are the specific trajectory segments that the cobot did. And then, like you can see here on the graph, was basically the post trajectory of the cobot. On the green side, we have all the unscrewing tasks uh, labeled by the UC. So we had first um, 4 screws, and then we had the blue kind of grayish area here, which was picking in place one of the frames. And then we follow up with another screws being taken out of the assembly, and then finishing up the disassembly task by taking the internal frame. So imagine you have all this trajectory in the XYZ space of the two um, uh, trajectory. Then you can replicate those into other robots by adapting the two frame, or what we call a base frame of the end effector of the robot. So we replicate that by translating and rotating the base frames based on the exact position that the other robots are in the space. So here on stage 3, we had the cobot experiment performing the entire disassembly process. And then on the figure B, we had the exact program being replicated in 2 different robots with different kinematics, different dimensions, and different position in space, uh, doing the exactly same process. And then think about you're dividing the tasks between uh, different robots, so different resources. Now we can start playing with how you're actually doing the scheduling between the tasks, and then moving it up into a large scale production. So after doing some of the physical disassembly, you start realizing that we had some variability how we position the robot tool with the object. So meaning that if I'm looking at the piece right now and I'm trying to position the cobot tool and the factor with the piece, I might have some accuracy on position that leads me to deviate sort of like from the center point of the component that I'm trying to grab. So in the figure A here on the screen, let's say that I position the cobot tool and the green dot, and then the yellow line is the center line of my component. And now if I send the cobot to close the gripper, and the cobot will force the entire assembly towards the center, the green point, and then it will bend my assembly, and then I will move up again. It will damage my part sometimes, and then we'll start creating problems such as interference or collision that might damage my parts or even stop the entire process. And we don't actually want to that. So, and also depending on the position that the component is in the space related to the human, we had different sort of variability as well on the positioning. So we kind of want to decrease that deviation, and we also want to account for different factors that those those variables in the process might be affecting the positioning. So I started we came up with this cognitive evaluation framework, whether we were being evaluating the human as the interactive component, the cobot as the tool, and the task as being all the assembly and the difficulty of the disassembly process. So on the cobot, so we want actually have this entire framework integrating all these 3 components, so we can start analyzing what are the specific variables that are influencing my error or positioning in the space, that we can decrease that and have like a enhanced trajectory for our cobot. So we started looking at the cobot and task. The 2 parameters that I studied was in the task workspace was based on the distance between the cobot and the object. So depending how the robot base was far away from the object, meaning that the cobot kinematics will kind of difficult or decrease difficultness of the process, and also the complexity of the disassembly task could be also measured by the script score. So I had evaluation based on the commands that we were using to accomplish the disassembly task. On the cobot side, because I didn't want to have like a very detailed evaluation on each the points in the space based on the robotic kinematics, I kind of summarized into how how fast the cobot could perform this entire cycle, uh, kind of relating to the difficultiness of the task. Then on the human side, we had uh, the programming time, so the total amount of time that we used to program the entire cobot script. Then we had the decision time, where the human was idling when he start from the starting point. He did the first command line until the end command line. So that idling time of he deciding which command should do or which position uh, and how to position the cobot in the space, that was the decision time. And then we had two other sensors that we were kind of measuring the engagement of the human. And you can see here in the bottom is one of the example of we measuring the engagement of the human. So that engagement metric was based on collaborators from Korea, whether the eye gaze was kind of facing the camera. So we put two cameras, one in the cobot teach pendant, so in the controller of the cobot, another camera in the object. So what, while the the programmer or the human was having issues with the controller, we will have a higher. We assume that we will have a higher engagement on the controller. Rather, if it is positioning, and he would be paying more attention in how to position the cobot with the object. So after getting some uh, data from multiple students programming the same task, so using the same kind of lead box, we had a set of experiments that ran through experts and beginners, meaning that beginners had never had contact with a cobot or had once or twice, and experts was already people that knew what are the commands that um, the cobot could do, and it was had some sort of like a long experience with the cobot. And then it's based on those parameters, I kind of we started to realize that beginners experts could be branched out into two big groups based on their data um, behavior. And then I started thinking that we could actually group those data and use that to train a positioning error. And then if we get this group kind of a error effect, and then we can tackle to decrease that positioning error. So the way we would be calculating that position will be combining all those human, cobot, and task variables into this equation, where we have, let's say we are positioning the cobot in the point A, and then we are moving out of in the direction of point B. Now we have uh, a direction here forming the angle alpha with the normal of the component vector. So we want to decrease as much as we can the distance between the point B with the normal vector. So that normal vector will be our ideal movement, right? And then having that angle is the key kind of a process we want to know, so we can reduce that error. So by calculating um, a new vector to accommodate those errors, we could use that angle multiply by the angle that we had the direction. So we program the retraction angle, retraction vector. Then we multiply by that alpha angle because alpha, and then by the normal, we had um, a new trajectory that will accommodate as error. So one grouping those vectors, I could actually uh, kind of decrease the deviation from the human positioning on the cobot on the bolt, and then trying to, if you can see here on the graph, the left side is the human program trajectory, and then the right side is the enhanced trajectory, where I want to pause here for a second, um, and then I want to show, oops, I want to show the difference between those two. If you see here on the human trajectory program, we had the retraction angle trying to go away from the center. And then now here, the enhanced, let's call it enhanced hand guided trajectory, trying to push backwards the trajectory towards the center point of the hole. So we are trying to grab the bolt in that way that we are moving, kind of adapting the trajectory to always give the bolt into the centerpiece of the hole. And now we'll kind of decrease that error deviation that we were seeing. However, that kind of those groupings did not have the good um, accuracy on how we could deviate. We had a lot of problems on how to actually measure the impact on the regression on the trajectory and the accuracy of the deviation. So there's a lot of rooms to studying there. And what are the other variables that are actually affecting the trajectory as well, while the human is interacting with the cobot. But just thinking about that, that's basically our low-level planning, and it's not really smart enough that we want to scale up that trajectory planning to automated disassembly line, that just by looking at incorporating the human kind of a decision making and the cobot trajectory. So what the second part of my research is more on the high level planning, whether we have this entire assembly level, and then we want not tackle the minimal errors on how to position the robot there, but how to optimize the tasks within one assembly file. So we want, in summary, we want to have the best sequencing of tasks to be performed in a way that we are reducing even more the disassembly time. So how actually disassembly planning works in the real life? So first of all, we start with the assembly assessment, whether we have the assembly, either CAD design or have a CAD diagram, and then we start analyzing all the part connections and how we will start the sequences of that we can take from that assembly. And then we move down to the assembly sequence planning, where we'll be optimizing throughout our entire sequence uh, how we are changing directions between components, which component should go first. And then after we have our optimal sequence, we move down to the robot trajectory. So, which is the rest part of the beginning of the seminar. And then we have our entire robotic disassembly plan. So the biggest problem here is the initial state of our process steps, which is the assembly assessment. Why? Because it's still up to date, it's a manual process. So we cannot actually automate, incorporate some sort of like a framework that we can actually do in large scale for any other component. So like I said at the beginning, remanufacturers or anyone that is being recycling and reusing products, they don't have the product data. Or if they do, they don't have a methodology that you can read that data and then have all the disassembly sequences. So I was working on how to automate that assembly assessment by studying the CAD designs. So people has been actually studying how to represent that assembly assessment, and then we can branch in kind of two main areas. One is the graph representation, another one is the matrix representation, and from those two, you have we can have some sort of like approach for routing problems, and then we can start optimizing based on heuristics or any other matrix-based methodologies. So to have those two,
Ask a
uh,
sorry, I have to leave in a minute. So I just want to ask one question. This is Raj. So if you have the assembly instructions, would that
mhm.
help create the disassembly sequence?
Well, there's yes and no, because this assembly, even though it looks like assembly in a reverse way,
Huh?
there are components that you cannot disassemble after it's assembled, right? Like if you have a snap fit, how you actually considering disassembly that snap fit? So you need to do some sort of destructive process. So sometimes it's easier you don't destroy that component and move to a different sequence. So when we are talking about creating that sequence, it might be totally different from assembly side. It's not just reversing the process, even
Right.
though you can have in so let's call it the disassembly sequence space. So whether we have all the possible sequences, the assembly sequences will be just a composition of that space, just a partial um, representation.
Right. Okay. Thank you.
You're welcome. Okay, so I really glad that you asked that question. So it's really good that we understand that this assembly disassembly is kind of different, and then uh, the way people have been trying to come up with automated disassembly sequence, I've seen only actually two ways. Either you generate features between two components, and then you train a deep neural network saying that if you see that feature, so if you see a surface um, function, and then this is similar to other surface functions, you will always have that direction or that movement. So this is not really, let's say, representative because different features can be also removed in different ways. So let's say you have a bolt or a screw. The bolt you basically have the same feature in the CAD, but one you will be kind of rotating, the other one you might be kind of having applied force, so you destroy the threads and then you push away. So it's kind of different. So the way that I was thinking is by moving pieces around, so we would be recognize each component that we have and then having a collision test. So we'll be moving each of the components in the space and then creating we call it interference matrix. And then from the interference matrix, we'll start generating all the sequence and then represent them. So how do we actually create that component? So inside, let's say in a step file, we had for each assembly component, we have a piece of the file that starts from the hierarchy of faces a surface representation and call it as a closed shell. So everything that is state as a closed shell and every hierarchy below that represents that model. So if we take that representation, we can start copying those pieces into a cyber environment and then manipulate that in any CAD software. So we copied that component, start moving them in a space. So we change their position based on the vertex of each faces. And then we start having a collision test. So we have three actually outcomes from them. Either one piece, like in the first figure, we move the bolt inside the assembly. So we have interpolation. Or in the second figure, we have two components and they are moving but not interpolating the space, but only touching. So I call it as a surface contact. But for the sake of this assembly, it doesn't mean that you're actually taking those two things apart. And then lastly, the third outcome that we can have from the collision is when we are moving exactly the opposite way. So there's no surface contact, no interpolation, meaning that we can disassemble that component. So we start to sampling each point in space while we're moving, and then we can represent the interference of that component with another one by the equation that you see in the on the slide. And then at the end, if you compute, you either have one if the movement is interference throughout the space, or zero, meaning that it's not interfering, meaning that you can disassemble that component in a particular direction. So you have interference matrix built on top of that interference check that has a n by n size and then m size of directions. So let's say we have 6 directions, so x, y, z, positive and negative, and we have 10 parts. You will have for each direction a matrix 10 by 10. So 6 times 10 by 10. Then we start, so it's a 3D matrix, right? So you start realizing which components can be disassembled first. So we sum up all the column rows for each of those directions, and then we have a vector. And then from the vector, we realize what are the actually disassembly directions that we can take. So then we decide, okay, we have this set of components that can be disassembled this set of directions. Then we choose one. And then from that one that we chose, we remove that from the initial interference matrix, remove the entire row and column for each of the 3D levels. And then we update the matrix and start choosing the next piece to be removed until we have a one by one matrix. So thinking of all the directions that we can have, we can represent in two ways, right? So either we can represent as a matrix. So one biggest or one very famous representation is the precedence matrix you see on the slide on the top, which you have all the possible outcomes being one element of the matrix. And then I came up with this direct disassembly sequence network, which each node of the matrix is represented in the network graph. So they are also linked based on their component precedence, and then meaning that the first initial node you see on the left is the assembly file being with all the components together, and then the last node is all the components being disassembled. And then you have the sequence. Each connection you have from the initial node, so the node on the left to the node on the right, is one sequence. So just to have idea how big this network can reach. So this like clamp of 17 components, we have 100 thousand in about 1,300 sequences, right? If we include order sensitive sequence, meaning that if we choose one component and then we choose the second one, uh, and then reverse the order, is two different sequences. But so this is the number of sequence, but number of nodes might be even more, like 10 times more or 100 times more. It depends on how you're assuming the sequences. So imagine that you have a really complex CAD file or assembly that increase of sequences and nodes will dramatically um, use dramatically hard your problem on deciding which is the best sequence. So just to kind of have idea, I have like a graph here to show you how long it takes to generate the graph um, for uh, for multiple components assembly. So starting from six, let's say six components, will take 0.2 seconds, right? So it's pretty fast to generate all the sequence solutions. And then if you have about, let's say, 16 components, will take more than 1 day to compute all the sequences. So it's not really smart we do it and we compute the optimal sequence in the deterministic space just because it's really hard to generate. So one branch of my work has been also optimizing how we can actually represent or generate those sequence even faster. So I came up with this um, sort of like multi-step methodology that we can actually group the components into sub-assemblies, even though it's not a real subassembly for assembly perspective. It is subassembly for disassembly perspective, but it's easy your calculation how the nodes can be explored throughout the sequences, and then you can kind of dramatically reduce that computational resource. So meaning that instead of we computing a 16 components at once, we can compute four components, four, and then integrate all of them together in one multi-layer network. So then we have we reduce from 1 day of computational time to maybe half a minute. But there's actually a really big problem when we apply that in practice because just to realize those sequences in a car, for example, which has more than 1,000 components, might not even be possible yet. So how people actually do the disassembly optimization? So they use heuristics, and then I'm just putting here one uh, heuristics that I use for sequence optimization, which is very famous for robotic disassembly planning, is the B's algorithm. So basically, you had the object function, which usually we are trying to reduce disassembly time. So we have disassembly task time, we have all the moving cost of the robot, we have penalties for tool chains and also direction change through the robot. And then from that object function, we are just constraining the sequences based on interference matrix. So how the heuristic approach does, it generates one population of sequence. So for the B's algorithm, it generates what they call it scal B's, and then the scal B's will branch generations, and then you increase the B's in that each of the scal B's, and then you check for the best B or the best sequence in that population, and then you start mutating those sequences by changing order or either changing direction or even mixing up the order of the sequence for each of the population, and then you combine at the end of some interaction number what are the best sequence that you found. But for each, so you generate one entire sequence at once and you check the feasibility. So just for you have idea, how long does it take the sequence optimization model? So for this part of 9 components, I came up so the B's algorithm has different parameters you need to set up at first. So you need to set up how many population you want to generate in parallel. You also need to set up how many, what is the size of the population, and so on. So imagine that you had multiple parameters, and you are checking also how many interactions you want to do it. And then this can actually take, so I had a set of 30 experiments parameters that I was changing throughout to see how the optimization works, or the minimal function will behave throughout each of the parameter selection and also the processing time. So I have here on the left graph here, kind of the optimization or the improvement of the solution in the yellowish, orangish, the improving from the initial solution to the current solution, and then the improvement from the initial to the end solution on the bluish. So it doesn't really change if you change parameters, but it dramatically changes the execution time if you don't do a good job on selecting the parameters. But if you compare the reaching the optimal sequence with generating the sequence, it's not, there's a big gap in there that so for most of the experiments, so I don't know, you guys cannot see the gray area just because it's really, really small. How much time you need to take from the CAD to generate the interference compared um, to the actually running the disassembly sequence optimization. It take at an average about 5%. So most of the time of the optimization model is just checking the feasibility. So let's say 95% is just checking feasibility, and so wasting a lot of time. So for that component, instead of you um, trying to reach a real-time optimization model, you will take sometimes 8 seconds, depending on the parameters and the accuracy of the approach, or you would even reach 30 seconds, which sometimes, if you're trying to actually do trajectory or task planning for a robot, it's not feasible. So I was trying to branch that sequence optimization to kind of a directions. One is trying to use a quantum computer to actually run the sequence optimization. So this is a routing problem, right? So there's a very famous way you can use right now in quantum computers, the QUBO formulation. And that for one of the particular kind of challenges here, you cannot use um, constraints for the quantum right now. And then you would kind of formulate a routing problem as in the minimization formula here. So first element is basically all the disassembly time function. And then the first two here is like a Sudoku constraint, whether you're trying to visit all the sequences and also one component only, right? So you have those two Sudoku constraints, and then I created this interference constraint, which is this function right here, trying to tell the model to say, do not create an unfeasible solution. This formulation right now works. However, there's a big problem on how to formulate that in the quantum computer, because the way that the quantum computer is built is in unity cells of 8 nodes, each unit cell, and the nodes are connected to each other unit nodes in multiple ways. So depending how you link the variable, the binary variable with the node, and how each variable is also connected, doesn't do a really good job when you're scaling up the problem. So meaning that if you have a unit cell or a node that's really connected to the other, the performance of the quantum computer will dramatically decrease. So right now, there's like some topological study how you actually uh, uh, map those variables into the quantum computing. So this is one of the kind of challenges that I'm trying to face right now. And then another kind of a branch of the sequence problem as well. I've been integrating human factors simulation software within the sequence optimization. This is part of a collaboration with IMK company that they had their own software. You can simulate the assembly or the assembly process, and then they calculate for you the human factors. But that calculation is not actually real time. So it demands quite a bit a computational time. So how do you actually sample that human factors in while you're optimizing the sequence so that the computer doesn't do a really bad job on actually telling, oh, this is the optimal sequence in terms of time and in terms of the human factor. So some sequences, so I sample just to have like idea what I'm talking about, have this simple disassembly process, and then the human was walking here around and then try to place the parts here as well. So he had walking paths, he had some manual tools, and then he had a given sequence. So sample 4 sequences. And then one of the sequences really did a great job on optimizing time. However, it wasn't giving the best um, human factors metric or ergonomic metric to that situation. So other sequences that might take more time might have a better uh, ergonomic metric. So you have to kind of balance that trade-off or how much you want to have of a good human factors process and how much you want to optimize your process. So there's a like a um, kind of a study how you're actually doing branching of the sequences in a smart way that you're not actually reevaluating bad ergonomic sequences and so on. And then lastly, kind of to wrap out, and hopefully we can have some discussion on this. So thinking that this assembly process is a very interconnected process coming from since manufacturing and use life of the product and then end use process. So it carries out a lot of factors when it reaches into your disassembly process. So how you can actually map out those variabilities that the part faces throughout the product life cycle and how that impacts your disassembly and how you can actually tackle those into the design phase that you will be saying, oh, I realize that uh, component or motor 1 and motor 2 has those variabilities. But if I change some component dimension or if I change orientation of a part, it will dramatically increase my disassembly process because XYZ factors. So, uh, so I hope you guys had kind of a big overview of my work and really happy to answer any questions or discuss anything about the seminar.
Thank you, Joe. I really enjoyed listening to your work again with the additional part, of course. Um, Thank you again for presenting your work. And any questions from the audience, please just unmute yourself and ask your question.
No, I just want to say that this is like kind of amazing that you're able to do this. So at first glance, it's not something that I would have considered doing because it's just too much variability. I guess my question is to make your life my statement is to make your life easier. Maybe the fixturing of how you fixture the components begin with will reduce a lot of that variability and complexity that you'll see.
That's true. It will dramatically reduce, especially for robotic applications, but at the same time, the product also carries the variability of the degradation of the components, right?
Yep.
So let's say you have motor and you have some screws, and then for some reason the screws is rusted, or you cannot even do the tool cannot engage with the screw because it's just open, right?
So, yeah, so I'm wondering how you kind of overcame a lot of that. I didn't want to say that because bring it up. Because
Right.
a human is going to recognize, okay, this screw is rusted. If I keep applying torque to try to release it, something bad is going to happen. Depending on how it's welded to the part from it being rusted, it could break the part if it's a plastic part or something, or you can strip the screw. And you got so much that you have to account for. I was looking at that alpha angle that you talked about, and you know, it's that goes all the way around, depending on how you fixture that part. So it's a lot. So I'm not a human will recognize certain things, like if I keep applying more and more torque, something bad's gonna happen. Whereas a robot, how do you?
Right. So I guess there's some um, some common rules that you have to assume at the beginning. Let's say you face like a big problem, and that's why the human and robot are working together, right? So let's say you face that rusted screw, and for some reason you need to destroy that screw, and you have to break it, so you cannot move forward, right? So that's the part that you have to accommodate that variability into the sequence planning. Say that this screw might have um, X percentage of being rusted, so you cannot move forward. So either you branch that sequence to go around that screw, or you ask for a human to help, and then you human will go there, modify that process. So instead of the robot will go unscrew, the human will go and destroy that screw. So you move
Okay,
forward. So
okay.
so there's a big study on that, um, on the sequence planning especially, and they use fuzz logic to kind of accommodate that variability. So you give some sort of like a probability of the component has defects. Okay, so that defect, if if you face that defect, so you will change either sequence or the process, and they also change the parameters of the the sequence plan. So meaning that it will take more time, or either you will change tools, and then you also have uh, a penalty for changing tools, a penalty for um, changing disassembly time as well. So it's kind of how you accommodate that, but the the biggest biggest issues is how you collect that data. It's not integrated from manufacturing to the disassembly site. So there's been going on also a big push from Europe to create what they call uh, design ecosystems. So European manufacturers, they are putting some partial data into that ecosystems that suppliers, remanufacturers, they can get usefulness of that data and implement on their production. So meaning that they know some design parameters, they know something about the product even before the product reaches your hand. So you're just tackling some of that variability. So in the process side, so you fix your product, so it's tight in a position, so you don't have the position variability, and but you don't know the model, right? You have sometimes that part suffers some damage throughout the 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 product life cycle, the use life cycle. So it might be missing one component. So how you actually perform better if you face that variability. So it's not
No,
just positioning.
great work as always, Jao. Great work.
Thank you, Leo.
Thank you for the true explanation. Any follow-up questions? Okay, if not, I think we are gonna be concluding just in time. It's 1:59, so I want to use this opportunity to again thank you, Joe, for presenting your work to us. I'm sure all of us learned a lot, and for everybody for attending this seminar. Thank you very much. And if you have any follow-up questions, feel free to reach out to me or Joe directly.
Thank you, Sarah. And yes, please feel free to send me email, and if you have any question or want to discuss, feel free to send an email.
Thank you very much. Bye, everyone.